So, okay. All right. So is my pointer visible?
Yes.
Yeah. Okay. So there is also a way to use a laser point. Okay. Okay. So we had two very good PhD students. Prashant, he has completed his PhD and is now a faculty at IIT-Kanpur. And Arihant, he's completed his PhD and a postdoc in University of Southampton. Some of the work we did was in collaboration, especially on cluster expansion and so on, or with Jishnu. So we had a very good team to begin with. Okay, Jishnu had lots of experience on batteries and so on. All the work which we have done on batteries has been supported by ISRO, right? Okay, so I had this title. I think Kantish was a bit worried about this title. Let me see how it goes. The title sounded a bit cryptic, I suppose. I wanted to have even more cryptic title on Goodenough quantum mechanics and adventures with bands, bonds, and batteries. Let's see whether the title fits the way I'm planning to unfold what I'm planning to unfold. Okay.
I'm sorry, I think you got muted. I'm sorry. I was clicking admitting someone and I got muted. Got you muted. Dr. Rajpala, by mistake, I muted you. I was letting someone in and can you please unmute yourself? Sorry for that. Sorry for that.
So this, okay. So let us, am I audible, Kantish?
Yes. I was admitting others and I request others to please mute themselves.
Unless you have something very interesting to say. Okay.
Please.
Right. So see, there can be questions in between. Okay. So I get this surreal feeling that I'm talking to myself when I'm doing this. So I don't mind if, Kantish, you can interrupt. I think you would know when there's a question.
Sure.
So we can also do that, right?
So if that is so, I'll request anyone who has any query, they can raise their hand, but please otherwise keep yourself muted. And then if you have any query, you can raise hand, you can also open your video and then you can ask questions.
Yeah.
If that is fine.
All right. Okay, so let us get started. Okay. So is this thing is the title visible?
Yes.
Yeah. Okay. So Kantish, maybe you can stay unmuted so that if there is something you can respond. All right.
Perfect.
So the main challenge we are trying to address world over is about energy. Okay. So there are different aspects of this energy problem. Energy as such is not a challenge. Okay. Because if you look at the amount of solar energy available, that is more than enough. But what is the main challenge is how to convert solar energy or some form of energy and store it, right? So this is particularly of big relevance in India because most of India is abundant in solar energy, but there are some parts of India which is not connected to electrical grids. Even if they are connected to electrical grids, the grids become operational only in the night time. So you need, when the sun is available, when you can capture the energy, you need to have a way of storing that solar energy that is stored. Okay, so electrical storage, energy storage is a very big problem. And if you look at many solar farms across India, if you use, let's say, the cost of batteries, okay, is almost as much as the money spent on the solar cells. So typically the batteries that are used are lead acid batteries in India, especially. They have a long history, but lead is a big pollutant if it gets into the ecosystem. So India is abundant in zinc, for example. There are lots of effort to make zinc-based stationary storage system. So the way I'm planning to, the main audience I'm addressing students. So I would try to tell what are some of the big open problems in this area and who are some of the researchers, and I will also direct you to some of the important papers in this field. Okay. So one of the big areas of research is if we can get a stationary storage device with zinc, okay, because zinc is, India has a lot of zinc in this area, lots of work is being done in this area. So there is also two approaches to converting chemical energy into electricity. One is the title of the topic of this lecture, which is the lithium-ion batteries. That is one thing. Almost everybody has lithium-ion batteries in your cell phone, in your laptop, and so on. Even though there is not much of activity, you don't hear something about fuel cell, I feel this in the long term, this is going to be very competitive. Okay, so there is a joke in this fuel cell community that a fuel cell community says that fuel cells are going to be in the market. They've been saying this for 60 years and so on. Okay, but still, this is a very serious contender. But for in certain applications, okay, especially in transportation sector and so on, right now, lithium-ion batteries is the main way to obtain from chemical energy to electrical energy, to get electrical energy. All right. So again, as I said, there is the main challenges in energy conversion and storage. So you have lots of energy available in the sun. What we're going to be talking about is how to convert solar. I mean, everybody knows, I mean, if you look around, there are lots of solar cells around. Solar cell is converted and you can store that energy in the batteries. And there is also another way of generating chemicals. Okay, you can capture the solar energy and generate hydrogen directly. Okay, this is the solar. Both these things can be done in what is called photoelectrochemical system. We are not going to talk about that. Our group works a lot in this area. There is another way to generate hydrogen. One is you can first convert solar energy and store it in, let's say, in a battery, and supply that electrical energy into an electrolyzer, okay, using electrochemical means, and you can generate hydrogen. This hydrogen can be supplied to fuel cell, and you can obtain electrical energy. The hydrogen has lots of uses. You can also use it in an internal combustion engine, get mechanical work, or supply to chemical industries. Okay, so these are some of the dominant themes. Lots of research is going on all these themes. So the reason we are talking about lithium-ion batteries, one of the reasons is the Nobel Prize in last year was awarded to these three gentlemen, Goodenough, Whittingham, and Oshino. Okay, so in fact, the composition of this team tells you the nature of research that is consequential. Goodenough was a physicist by training. Okay, he did his BS in mathematics and PhD in physics from University of Chicago, and then he took to material physics and material chemistry. Whittingham is by training a chemist. Okay, and Oshino spent most of his research career in Asahi Chemicals. Okay, so in fact, both these people, Whittingham spent a lot of time in ExxonMobil, and he spent a lot of time in Asahi Chemicals, and Goodenough worked a lot on engineering applications. Okay, so Oshino had an engineering approach to a problem. Okay, so I'll clarify what you mean by engineering approach. Whittingham's approach was always in terms of some chemical approach, and Goodenough used some of the constructs, okay, some of the concepts that are typically used in physics community, and used it to design batteries, right? So this is an extremely insightful paper, which has gives you a lot of history on lithium-ion batteries. Goodenough, few years ago, he was very fit to even play in IPL, right? But last few years, he's 98 years old. Okay, last few years he was not so fit. So the Nobel Prize lecture was delivered by Professor Arumugam Mandiram. Okay, so he is of Indian origin. He did his PhD in IIT Madras. He was a chemist, and he was a postdoctoral fellow of Goodenough when Goodenough was in Oxford. So Mandiram delivered the Nobel Prize lecture. And it also, the work of Goodenough, there are three main works that are highlighted here. So I'll elaborate more. This is on layered cathodes. Okay, so LCO, most of your cell phone batteries have this material. All right. So this is a very important material. Much of this work was done by a Japanese, a postdoc of Japanese origin. And there is certain kinds of very less expensive cathode material called spinel materials. This was a postdoc from South Africa who did this work. And of course, Mandiram of Indian origin worked on certain kinds of cathode material called LFP, lithium ion phosphate, and olivine phases, and so on. Okay, so it also talks about the nature of research. Okay, nature of research is not only interdisciplinary; it's very international. Okay, so to do good work, you have to be able to collaborate and collaborate across continents and so on. Right. So we'll elaborate. This is a very good paper that you can follow it up. This is it's a review and has a lot of historical insight. Right. So much of the material. Some of the material I've taken from this. Okay, so let's start here. So the first thing is the title visible? Because I keep getting this thing.
No, it is visible. It is visible.
Okay. So how not to make a battery? Okay. So I would want some response. Okay. You can type your response. So let me see whether I can see. Okay. So here we have a. Okay. So here I have a cadmium metal rod and have a silver metal rod. Okay. So if I dip it into an electrolyte, let's say containing cadmium nitrate and silver nitrate. So if I look at, so this is something which you have seen from high school. Okay. So you have reduction potential of cadmium, reduction potential of silver. Okay. So you have seen from your high school knowledge, EC minus EA. Okay. So this is the cathode. Let's say this is the anode. So would I get 1.2 volts? Is this a good way of making a battery? Does anybody volunteer to answer? You can unmute yourself and then, or you can first raise your hands and Kantesh can unmute you and then we can hear your answers. Is this a good way? See, this is a good kind of a question. Okay, yes or no? You have 50% of getting a right answer. Okay, 50% probability of getting a right answer. Does anybody want to volunteer? Is this a good way of making a battery? So I can think that cadmium will get oxidized and form Ce2+, and silver will get reduced. And would I get a battery voltage of 1.2? Any answers? Anybody ready to raise your hand and answer?
I can give an answer. I think others.
Or you can even type. Somebody has raised your hands?
So many are saying no.
Okay, no. Okay, so that is, see, I always ask when towards the end of the semester, yes, no, maybe I don't care. Okay, so you've come here, so I don't care is not an option. So why no? Okay, so more interesting is, do you want to give some reasons on why you want to say no here? What is the problem with this geometry? Anybody wants to raise your hand and answer?
Yeah, maybe Akhil and Sankalp, they can maybe unmute and answer if.
Hello.
Yeah, you're audible.
So here the CD2 plus might go and deposit on the Ag silver, and that would there will be deposition of CD on the silver. That can happen.
Okay. So what you are what you are trying to say is CD2 plus will want to stay oxidized. Okay. So what you are probably trying to say is the following. Okay. So when let's say CD2, so effectively what you want to do is you want to oxidize CD, okay, and reduce silver. But the way you don't want that to happen is the silver in the solution should not directly collide with this electrode and oxidize. Okay, so cadmium can get oxidized and silver can get reduced on the cadmium electrode. Okay, so when you do that, there is still energy release, but that energy release is not going to give you electrical energy. Okay, the energy release is going to give you thermal energy. Okay, so you don't want that to happen. So the right way to make a battery is you want to separate the two reactions. The oxidation reaction should be separated from the reduction reaction. And there is something called a salt bridge, which you might have heard from your high school. Okay, so this is a better way. In this geometry, you have only cadmium dipped into a cadmium nitrate, silver dipped into silver nitrate. Therefore, the reduction of silver ions by collision with cadmium is not possible. Okay, so the important thing, so in this is a reasonable geometry for making a battery. Okay, so the main take home message is electrochemical reactions or redox reactions and oxidation and reduction occur at different electrodes. Okay, so this is the way to convert the chemical energy into electrical energy. And one of the main themes which we are not going to elaborate here is both batteries and fuel cells are not limited by Carnot efficiency. Okay, most of your internal combustion engine from your thermodynamic classes, okay, are limited by Carnot efficiency. Okay, so one of the important goals why we want to do energy conversion using batteries and fuel cells, it is not limited by Carnot efficiency. Okay, so the next question is what exactly do we mean by when we say we are measuring a voltage? Okay, so typically we'll measure a voltage with respect to something called standard reference electrodes. So what does a reference electrode here? Okay, this is your, let's say, a test electrode. This is your ideal, one of the reference electrodes. So let's understand what you mean by a reference electrode. Again, this is something which you've seen from your high school. Okay, so what does a reference electrode do? This is a standard hydrogen electrode. So the standard hydrogen electrode tries to keep this equilibrium. Okay, so hydrogen gas, which is let's say comes from a cylinder, it's dissolved in an electrolyte, and this equilibrium is maintained in this electrode. Okay, so when you do that, what we try to maintain is the chemical potential of hydrogen, which is determined by the partial pressure of hydrogen. Okay, if you control the pressure of hydrogen, you are able to control the chemical potential of hydrogen. Because this equilibrium is maintained, this balance is always maintained. Okay, so what controls the chemical potential of proton is the concentration of proton. If you maintain this is the chemical potential of hydrogen is maintained. If you maintain the concentration or the activity of protons, the chemical potential of protons is maintained. So by maintaining these two, I have a control of the chemical potential of electrons in this electrode. Okay, so when I say I'm measuring a voltage of this electrode against the standard reference electrode, what I mean is I'm measuring the chemical potential or the energy of the electrode in this test electrode against this electrode. Okay, because by maintaining these two chemical potentials, I know what is the energy of the electron in the reference electrode. Therefore, I have a complete measure of what is the energy of the electron in this test electrode. Okay, so that's an important concept to understand. So why do I use a platinum? Platinum is a very good electrocatalyst for maintaining this equilibrium. Okay, so yeah, so that's what we try to maintain. Okay, and also you might have seen in your high school the way we can talk about this delta G of this electrode. You maintain by saying NFE, minus NFE. Okay, so N in this case denotes this, and F is a Faraday's constant, and this is the electrode potential. Okay, so electrode potential is a thermodynamic potential. It's a so it is indicative of the free energy of the electron. Okay, so it is function of temperature, pressure, and concentration. Right. So if you have questions, you can raise your hand and ask. And another thing which you must have, if you want to change the electrochemical potential here, supposing that can be attempted, the electrochemical potential is maintained by another redox reaction. Okay, so that you might have seen something called a Nernst equation, again from your high school you might have seen, by maintaining by different concentration of a reductant and oxidant, you can maintain the electrochemical potential here. So a voltmeter measures this electrochemical potential if an equilibrium is established here using these two, using a redox couple. I can measure mathematically I can represent the electrochemical potential using a Nernst equation, and I can measure the electrochemical potential of this test electrode against a reference electrode. Okay, so that's what I try to do. So these reduction potentials have an intuitive sense. So if I look at this from a periodic table, so this is from a standard reduction potentials, which you can obtain from a high school electrochemistry chapter or from any other electrochemical book. So if I look at reduction potential of lithium, okay, so the reduction potential of lithium is very negative. Okay, so I just okay. So it is very negative. So if I convert this into free energies, the negative electron as a negative charge, I can, so this free energy of this process, lithium plus electron, will give me a very endothermic reaction. G is equal to, if I multiply by negative charge of the electron, this will be a very positive number. That makes sense, right? So this is an alkali metal. The alkali metal will always want to stay as a cation. So adding an electron to this alkali cation is a very endothermic process. As opposed to that, other extreme is gold is a very electronegative atom, gold or chlorine. Okay, adding an electron to gold must be an exothermic reaction, right? If the reduction potential is very positive, multiplying by a negative number, the charge of an electron would give me a negative number, which is indicative of an exothermic reaction. Okay, so when you say some redox couple has a very negative reduction potential, that means the reduction of that species is very difficult. Okay, so that makes chemical sense. Okay, these are all very electropositive elements. The reducing this is very hard. But whereas when you go to noble metals like gold and silver, it is very easily reduced. Okay, so gold is one of the most electronegative elements. Therefore, it can be very easily reduced. The gold 3+ can very easily be reduced. Therefore, it has very positive reduction potential. Right. So this you can understand from the periodic table why the reduction potentials are what they are. Okay. So if you look at the timeline, okay, so batteries is not a new problem. The first Volta Pi, okay, so that was demonstrated by Volta in 1800s, and the lead acid battery again by Planté he did it in 1860s, and fuel cells also came long time ago. Okay, but lead acid batteries at least are commercially viable. So there are lots of battery chemistries that have come across, but the real battery revolution started, let's say, from 1980s. Okay, this is when the Sony Corporation, okay, so came out with a commercial lead acid lithium-ion battery and put it in cameras and so on. So the last 40 years is when lots of work, commercialization of lead acid of batteries took place. Okay, so what you see in car in 80s when we were kids and so on, those were stationed. Even now, all the batteries in most of the cars, okay, have lead acid battery. But electric vehicles, okay, Elon Musk, everybody must have heard about Elon Musk. Tesla cars, okay, so they the big thrust of Tesla cars are in terms of lithium-ion batteries. Okay, so even in a Tesla car, okay, 1/3 of the weight of the car goes into batteries. Okay, so that's not very. You want to use the car for driving around people and not the batteries themselves. So there are lots of challenges ahead. So we will talk about lots of new materials. What are the new battery chemistries that are promising? Okay, so this is I want to take you from fundamentals of electrochemistry batteries all the way to frontiers, okay, and so on. So why lithium is used? Because it has the highest reduction potential, okay, the most reduction potential. So we'll see why this is important. It is the lightest metal. Okay, even with a lithium-ion battery, if you want to use only a battery to drive around the car, even with a lithium-ion battery, the battery weight is a lot. So supposing if you use a lead-acid battery, it would be just impossible. Okay, so the lead-acid battery, which is used in cars most of the time, is just for starting. Okay, and for running, if your car is switched off, you still want to operate the light, you use lead-acid battery. So that is a small part of the battery. Okay, for most of the cars. Okay, a small part of the cars, but in an electric vehicle, okay, you want to use a battery which is very light. Okay, so lithium is the lightest component, lightest metal that can be used. Okay, the charge density is also significantly high. Okay, so we will see. Okay, this is almost 20 times more than what a lead acid battery can give. Okay, another thing which you want to keep in mind is these are all what are called large area devices. Okay, so you want to be using, if battery is the next petrol. Okay, so you are going to be using lots and lots of these elements. So if you're going to be using these such elements, you want to make sure that you are not. This is for every engineering student or an applied scientist. Okay, this graph should be etched in your mind. Okay, so here on the y-axis we are talking about abundance of elements. Here on the x-axis you have the atomic number. Okay, so here we are talking about very rare metals, rhodium. Okay. See, these are the metals that you use for your rings. Okay, if you're dating, if you want to impress, okay, your person for your Valentine's Day or your wedding ring will be made up of gold, platinum, and so on. Okay, you don't want to be making a large area device with these rare metals. Okay, but lithium is not that abundant, but at the same time, it is not that rare also. Okay, but once if you use more and more lithium, lithium might be the next goal. Okay, so that's very important. So, so any large area device that is made with rare metals is up for grabs. Okay, there is going to be a lot of technology change if you are going to be using these metals. For example, catalytic converters. Okay, use rhodium. Okay, which is underneath every car. There's a catalytic converter. Okay, which is used for pollution control. So there is lots of work that is being done for replacing rhodium with making a catalytic converter without this. Okay, expensive. So this is an important graph which you should always have in mind. Okay, and so let's go get ahead. So how does the lithium-ion battery work? All the lithium-ion battery is made in the discharge state. Why do you do that? For example, if you have a charged battery, okay, if you don't use it, it is always in a high energy state. There is going to be the energy of the battery is going to keep coming down. Okay, so if most of the lithium-ion battery that is given to you is going to be given to you in a discharge state. So you want to use a power supply to charge the battery. You can't get a power out of it. So you want to charge the battery. Okay, so the voltage of the battery is very low in the discharge state. When you charge the battery, what you're trying to do is you're going to increase the voltage of a battery. Okay, so this is the most common battery chemistry. What you try to do is, so there is some sign conventions. I'll try to make it intuitive. Okay, so there is this called a negative electrode. So the most common negative electrode is graphite. Okay, so when you charge the battery, what you have done is you have moved the battery from the positive electrode to a negative electrode. We'll try to understand why is this called a positive electrode, a negative electrode. So what you try to do is hello, there is some background one. Is it possible to mute? All right.
Ashok Umiredi, can you please mute your mic? Ashok, please.
Unless he has a question. Okay.
Yes.
Okay. So what you have tried to do is when you charge the battery, you have moved the lithium from the positive electrode or the cathode in this case to a negative electrode. Okay, so by this process, you have increased the energy of a system. Okay, so when you take the lithium from the transition metal oxide, cobalt oxide, when you moved it to and put it intercalation means the technical term, where I have, these are graphite, this is graphite, let's say. I have put the lithium into the graphite, in between the graphite layers, okay. So when I've done that, I've increased the energy of the system, okay. So I've raised the voltage, and then what I've managed to do is I've removed the lithium from the cobalt oxide, lithium cobalt oxide, and then put this lithium, moved it across the electrolyte, and then intercalated into the graphite, okay. So, and then I have formed this compound. So this is at a high energy state. So, and I have used a power supply, external power supply to charge the battery. And then when I discharge the battery, what I have done, the sign conventions that we use will make sense here. So the electronic current goes, the electrons go in this direction. I have, so let us do this, okay. So the electronic current in this direction, therefore the conventional current is in this direction. That is why I'm calling this as a negative electrode. All right. The conventional current in this electrode, therefore I'm calling this as a positive electrode. And then during discharge, what I have done is I have, just to do this again. Okay? So I have lithium ions in the graphite material, which is intercalated, and that the voltage comes down as the battery discharges. The lithium ion goes through an electrolyte. Electrolyte is a ion conductor, okay. Electrode is an electronic conductor, whereas this is an ion conductor. So the lithium ion goes across an electrolyte, gets again intercalated with the transition metal oxide, okay. This is an exothermic process, okay. That's why I'm able to get energy out of the system. So during a charging process, I have done an endothermic process. During a discharging process, I have an exothermic process, which has given rise to give rise to an voltage. Okay, so this is the bare minimum thing. Okay, this is almost at a high school level, which we should understand. Okay, so here you have a graphite, which is the most common anode. Okay, which is used in most of your cell phone batteries. Again, you have another intercalation material, which is lithium cobalt oxide, which is the cathode material. This is a positive electrode. This is a negative electrode. Okay, so if there are some questions, I can answer now also. This is fairly elementary. Okay, at least this we should all be in the same page. Okay, the overall voltage is E positive minus E negative. Okay, so all right, and this is typically you may get about 3 to 4 volts from this kind of a lithium cobalt oxide and a graphite electrode. All right, so what is this is we are going into a more greater detail. These are all research areas. I'll also indicate what are the important research areas here. Okay, so so I have an electrolyte. So I have 2 electrodes. There's an anode and a cathode. So I said that in a charged battery, the energy of the electron is high. Okay, that means the chemical potential or the Fermi level. These are all same terms. Okay, the chemical literature, what you call the electrochemical potential, is the same as what is used in physics or material science called Fermi level. In a charged system, the energy of this electron is high. So this is, I'll first talk what these acronyms. So it's called highest occupied molecular orbital. Okay, the molecular orbital means it is orbital means it's the wave function for a single electron is called an orbital. Okay, if you have a hydrogen atom, you might have heard as s orbital, p orbital, d orbital, f orbitals, and so on. An orbital means it is a wave function of a single electron. Okay, molecular orbital means these are orbitals formed in a molecule. Okay, so these are the molecules that form the electrolyte, or that's what I'm indicating here. These are the molecular orbitals of the electrolytes. Okay, highest occupied molecular orbital. That means this molecular orbital has already electrons in them. Here, LUMO means lowest unoccupied molecular orbital. Okay, so these are empty molecular orbitals. So when I contact this electrolyte into the anode, because the energy of the anode, the energy of the electron of the anode is higher than that of the lowest unoccupied vacant molecular orbital. What can happen? There can be electron transfer from the anode to the electrolyte. Okay, so whenever there is such an electron transfer from the anode to the electrolyte, for example, if you have this electrolyte, if it's say it's an aqueous electrolyte, say water decomposition can occur. Okay, you don't want that to happen. You want the electron transfer to happen only between lithium ions, okay, and not to the other electrolytes in the electrolyte. Okay, so there are supporting, there are other chemical components of the electrolyte, which doesn't involve lithium. You don't want the electron transfer to occur to that electrolyte. For example, in your lithium, the lithium-ion battery that you have in your cell phone, if I had water as an electrolyte, what would happen is water decomposition would occur. Water would decompose into oxygen and hydrogen. That you don't want to be occurring. We'll see what happens. Supposing if you had an aqueous electrolyte in your lithium-ion battery, or let's say, so in a typical lithium-ion battery which you have in your cell phone, you have certain non-aqueous systems, okay, some organic electrolytes. Even for those organic electrolytes, LUMO can be at a lower level compared to this level. So there is some decomposition that occurs, and then you have an insulating layer, okay, which is formed called solid electrolyte interface, okay, SEI. Okay, this is one of the mysteries. Okay, this is a fortuitous. We are lucky to have the solid electrolyte interface. Okay, else we cannot operate a lithium-ion battery. Okay, even though, so what is a solid electrolyte interface? Let me clarify. So in your lithium-ion battery, you have organic non-aqueous electrolyte whose LUMO is still lower than this level. Even though it is lower, because it is lower, there is some decomposition of the electrolyte that is occurring, and the decomposition products form an insulating layer called solid electrolyte interface, which prevents further decomposition. Okay, so that is what is formed. So by then, slowly, this energy level comes down. It will come down below the LUMO, that is the lowest occupied molecular orbital. Therefore, there is no driving force for any more electron transfer between the anode and the electrolyte, okay, the organic electrolyte. So the same thing can occur. This is called an anode SEI. Okay, so this is a very big open problem. What is the composition of the electrolyte? How does it work, and so on? It allows for lithium to transport, but it doesn't allow for electrons to transport. So likewise, a similar process can occur in the cathode. So again, there's a cathode SEI that is formed. So once the cathode SEI is formed, there's an insulating object. Therefore, there's no more electron transfer. So finally, the cathode, okay, would be at this level, and the anode at this level, will be at this level. There's no more electron transfer between the electrode and the electrolytes. The electron transfer will be only from the electrode to lithium salt. Okay, so this the difference between this two levels, okay, is called the open circuit level. Okay, so this level, that is more or less the LUMO of the electrolyte and the LUMO of the cathode, it gives you the open circuit electrode. Okay, all right. So you want to have as high as open circuit electrode. Again, therefore, the difference between the lowest unoccupied molecular orbital and the highest unoccupied molecular orbital should be as high as possible. If you use water, this difference between HOMO and LUMO of water is only 1.23. Whereas if you have an organic electrolyte, it can be 3, 4, and so on. There are solid electrolytes. We will come to that at a later stage. We are trying to increase this difference as much as possible. Even you can get it to 5. Okay, so if you, the greater the difference, the greater is the open circuit potential. So what are the important desirable properties of a battery? First, you want to have as high a potential for a battery. Okay, for a lead acid battery is only about 1 and so on. Okay, and that is an aqueous battery. Okay, you have water as an electrolyte. For in a lithium-ion battery, all the electrolytes are non-aqueous. So you want to have as high as a voltage as is possible. If you have 5, that is very good, okay? And then your capacity should be very high, okay? So the lot of research is to keep on increasing your potential that you can get from the battery. Again, it is the greater the potential, your difference between HOMO and LUMO should be greater, and you want to increase as high, the capacity should be as high as possible, okay? So one of the advanced electrodes which we have also working is called silicon electrode. Lithium itself can be an anode, and these are the important, the most common cathode is the lithium cobalt oxide, okay? This is the most cheapest cathode is the lithium manganese oxide, and LFP you will also hear, okay? These are the common commercially viable cathodes. The most common anode is the graphite, okay? The lithium ion battery in your cell phone will have the, most likely it will have graphite as the anode and lithium cobalt oxide as the cathode, all right? All right.
Hi, Raj.
So again, yeah.
Hi, Raj. I have a question.
Yeah.
Shobit here.
Yeah, sure.
So, your discussion about SAI, right? Why does SAI play an important role in anode compared to cathode?
See, it is not an, see, both in the first place, okay, it was recognized, the role of SAI was recognized more in the anode. Okay? It is not that it doesn't play a role in the cathode side. In fact, in the last 5 years or so, the cathode, the role of cathode SAI is becoming more and more important. See, another important role in anode SAI is the SAI also plays a role in suppression of dendrites. I'll come to this question at a slightly later stage. Okay, so I'll answer this at a slightly later stage. Okay, so it's just to clarify. Yeah, go on.
Yeah, so I thought that SAI is normally happening because when we have pure metal like lithium or pure sodium.
Not true. Okay, so it is not really.
It can happen
even
also
when you have a graphite, there is an SAI there. So the most of the SAI studies came out was in the context of anodes. Okay, so in the last 5 or 6 years, even we have done some work where cathode SAI is also becoming the role of what is the role of cathode SAI is also becoming important. For example, if you have sulfur as a cathode, okay, there lots of work has been done on SAI on cathodes and so on. Okay, so I'll come to this because I want to introduce a term called dendrites. I don't want to do in this slide, but I'll come back to this question later. Okay, all right. So just to understand why is even here some quantum mechanical concepts called HOMO and LUMO was introduced. So I will get to why I call this one part of the title Goodenough quantum mechanics. Okay, so I will come to that. Okay, so long ago, Dirac is one of the pioneers of quantum mechanics. Okay, so he said the underlying physical laws, large part of physics and chemistry means materials chemistry and so on. Okay, were completely known. Okay, so the physical laws which he was talking about are quantum mechanical laws, Schrodinger equation. All these things came in 1929. So he thought that whole of chemistry can be understood at that time. So at that time there was a materials engineer, okay, in 1929. So he was very excited. Okay, so these are the engineers who also who also keep reading a lot of sciences. Okay, so he knew the greatest advance in sciences. So he was very excited. He wanted to. He was interested in batteries. He wanted to design electrodes, batteries ab initio. That means from first principles. Okay, so a lot of engineering. Edison, one of the famous engineers. He was in early 1900s. He was commercially very successful engineer. There is an approach called Edisonian. Okay, that means you do lots and lots of experiments, lots of empiricism is involved. But this materials engineer was not an Edisonian. He was an engineering scientist. Okay, that's the education paradigm of IIT-Kanpur is on engineering science. You try to do a lot of engineering using sciences. So this is one of such engineer. So he wanted to design from first principle. So, but there was a chemist sitting beside him or her. Okay. So he said that a Schrodinger equation can be solved exactly for hydrogen atom. Okay, she said that that is helium here, not he or she here. Helium atom can be solved with difficulty. Okay, so this chemist told the materials interested, just forget quantum mechanics. Okay, you cannot design materials from quantum mechanics. Go back to your empirical way of designing materials. The response to which materials engineer told the quantum chemists and quantum mechanics said, forget quantum mechanics. Okay, so this whole situation has changed. Okay, so whereas a 21st century materials engineer claims that I am a quantum mechanic. Okay, I am no longer just a materials engineer, I'm a quantum mechanic. So what do I mean by that? So lot of material design is done in this. For example, work which we did, I'm familiar with these materials, so I'm using this example. Okay? Some of the materials that I use, it's not the thing that, I'm not saying that this is the frontier, but just because of a familiarity, I'm using these examples. Okay, so we use, so for example, there is a material engineering that needs to be done where I'm trying to find out the semiconductor electrocatalyst. So what you typically try to do is, I know that the entire material space consisting of semiconductors is has to be explored for finding an optimal material. Okay, so I screen for a band gap, I screen for particular kind of heterostructures, and so on. Certain properties have to be explored. Okay, so there is lots and lots of these possibilities, but I know what is my desired material, my desired material should have. Okay, so instead of doing thousands of experiments, I can do these experiments inside a computer called computational experiments using the fundamentals of quantum mechanics. Okay, and then we scan hundreds of materials, and we arrived at a handful of materials which had this desirable properties. Okay, this computational experiment or computational screening was done in our lab. However, there are companies, okay, in Europe and in US, okay, where this kind of experiments are being done. Okay, so lots of material engineering, for example, from 2000, there's a company which focuses only on lithium-ion cathode. Okay, using basics of computational quantum mechanics, they try to screen, and they say after screening for 2000 materials, they come up with a handful and give it to an experimentalist. Can you test these materials? Okay, so the experimental labor has been decreased tremendously. Okay, and then they try to see whether, ultimately, you cannot avoid experiments. So you have to do the experiments, but can you decrease the tedium of experiments? That is the goal of computational quantum mechanics. And then the last 3-4 years, with lots of big data, artificial intelligence, machine learning, this computational screening has been made more effective. Okay, so on top of computational quantum mechanics, the tools of machine learning, artificial intelligence are going to play a tremendous role, okay, in exploring new materials. So as students in 2020, you should all be aware of this important tool, frontier tool. That's why one of the goal of this is to make you aware of these tools. Okay, so what revolutionized quantum mechanics? Okay, the application of quantum mechanics to material science and engineering is what is called density functional theory. Okay, so this is a theory to obtain energies of surface processes and so on, intercalative process. That's what is important in lithium-ion batteries. What do I mean by that? Supposing a lithium-ion intercalates, okay, binds. Intercalation is let's say a fancy word for lithium-ion binding to a particular transition metal oxide. This theory, based on quantum mechanics, can give very good estimates of these energies. Okay, it may not give you the correct estimate, correct absolute energy of binding of lithium-ion to transition metal oxide, but it may give correct trends in energy. Okay, so the important thing to understand is trends in energy helps in material design. Okay, if you know what kinds of materials will bind too strongly or too loosely, okay, if the trend is obtained, then I can design materials with these trends. Okay, so what made density functional theory a practical computational screen? So early, when Dirac was speaking about quantum mechanics, he was all the information that you need to know was contained in the wave function for the system. Okay, this is a very hard to compute the computational time scales very badly. It's very hard to compute or scheme. However, if you can replace this, instead of computing a wave function, if you can use the density, electronic density, the computational scheme is decreased. Okay, even if you don't understand all these things, see, there is this when you register for courses. Okay, in IIT-Kanpur, at least there are at a given semester there's at least one course which will talk about density function theory. I am teaching a course. There's material science, chemistry department, physics department. Always have some course running in a given semester which elaborates all these things. This material contained here is elaborated in one semester. So don't be concerned if you don't understand this material. I'm just trying to tell, before you search, as students you're trying to search, you should know what to search. What are the important avenues which you should be searching. Okay. So Walter Kahn, he got a Nobel Prize in 1999, shared it with John Popel for developing this theory. Okay, so they developed this theory and implemented these theories in a very practical manner, so that materials engineering, chemical engineering can be done using these methods. Okay, so this is another looks like a busy slide. Okay, so I'll try to go. So we're running slow. We have to pick up speed. Okay, let's try to wrap up in 15 minutes or so. So again, this is from Arumugam Mandiram's paper. So okay, so you must have heard something called band structure in solids. Okay, so again, this is how what I'm trying to elaborate here is how qualitative notions of quantum mechanics can be used for understanding what materials can be used as a cathode, okay, for batteries. So what I'm trying to do when I construct a battery is I am trying to, this kind of orbitals are present in the anode. Okay, that is, electrons are located in the anode, and during the discharge of a battery, I am transferring electrons that are located in this band. Okay, what is a band? Band is a collection of molecular orbitals. Okay, this is where these electrons are. Okay, during in a charged battery, this is the anode of a charged battery. What I try to do is I transfer the electrons from these orbital or from these bands to these bands. Okay, so for example, one of the first cathode, okay, one of the Nobel laureates called Whittingham, he devised the first cathode called titanium disulfide. Okay, titanium disulfide is made up of a band that comes from orbitals of titanium, or it can come from orbitals of sulfur. So these, how do I obtain these bands? What I said from the previous slide, density functional theory now gives you a very all density functional theories implemented in packages, okay, computational software packages, which will help you, give you the position of these bands. Okay, so if I know the position of these bands, okay, from computational density functional theory, I have a way of estimating what is the voltage I can get from that particular battery. So the first cathode, which was developed by Whittingham, I think in late or 1972 or something, in the middle 1970s, was when I transfer the electron from, say, lithium to here. So this is lower in energy. Okay, so what am I plotting here? On the y-axis, I'm plotting energy. On the x-axis, I'm plotting density of electronic states. Okay, so what do I mean by that? The number of electronics levels, number of levels available for taking up electrons, okay, divided by energy is called density of electronic states. Okay, so you can just think about the axis as number of energy levels available. Okay, how many electrons I can take. If I have more, if this is more, that means I can take up more electrons compared to something with lesser density of electronic states. Okay, on the y-axis I'm plotting energy. When I transfer electron from here to here, my energy is less compared to when I transfer electrons from here to the most common electrode material used in the lithium ion battery, which you have it in your cell phone. Okay, so this is about 2 volts, but compared to LCO, lithium cobalt oxide, the voltage that you get from the first electrode from first cathode is much lesser. This is about 2 volts. This is about 4 volts. Okay. So what do? When I say what does the research involve in cathode? Okay. So I try to explore different cathode chemistry. Okay. To find out what can give you more and more voltage. If I have to get more and more voltage, the energy of my electronic level, energy of the bands that comprise the cathode has to be lower and lower. If the lower it is, okay, that is compared, let's say manganese, nickel and cobalt. Cobalt will give the most voltage because the cobalt band is lower than the nickel band, is lower than manganese band, which is lower than the titanium. Okay, so this is, and this can be obtained from computational quantum mechanics. What did Goodenough's important contribution is, Goodenough came from the area of physics. Okay, so physicists have are taught solid state physics even at an undergraduate level. So this way of thinking about lithium chemistry, okay, lithium ion battery chemistry, that is, a chemist would say that lithium ions would go and binds to this material. The chemists typically think in terms of binding energies. But what Goodenough, from his background in physics, he tried to interpret all this voltage in terms of band structure of solids. Okay, so that is one of the biggest contribution. It gave a conceptual framework to think about how to go from chemistry, synthesis of materials, to band structure of materials, to voltage that you can get from lithium-ion batteries. Okay, and then we can pick up speed. Okay, this I will neglect. So in addition to energies, what is also important is lithium has to go to the bulk of the material and bind. Okay, so the diffusion of lithium ions has to be also facile. Okay, the lithium has to diffuse very easily. So these materials also facilitate lithium ion diffusion. What are the materials I'm talking about? These are, let's say, lithium cobalt oxide, this transition metal oxide, have facile pathways for lithiums to diffuse. Okay, and so another thing, so this is more of Mandiram's work. So again, when you change the material, so from, let's say, iron oxide is one of the cheapest material, right? It just rusts. If you can make a lithium ion battery from iron oxide, the material is going to be, the battery is going to be very cheap. Okay, that is possible, indeed possible, but the conductivity is not that great, but the potential is not that good. Okay, so a lot of efforts was made to introduce other elements. Okay, and how to change, again, when you change the material, chemist typically, Mandiram is a solid state chemist, he changed the material. Goodenough had a way of going from material to bands of the material and then converting the bands of the material to voltage. Okay, again, these kinds of things is elaborated in this paper. Okay, more information can be done. So what I mean by bonds is chemist's way of thinking about when you change the bonding pattern, when you go from iron oxide to molybdenum oxide, from sulfates to phosphates, how do you go from bonding to bands and to voltage? Okay, that is what you should try to learn. Okay, so that is the conceptual design of materials. Okay, so the old Edisonian way of make it and measure it. Okay, that is very unproductive way of doing research. You should be able to have a conceptual framework for designing materials and so on. Okay, so again, so what is this is something from what we have done in our work. These are two graduate PhD students, and this is our collaborator in mechanical engineering, Professor Jishnu Bhattacharya. He is an expert in solid state ionics, and I'll also tell who is working in what in this area. There is, yeah. Okay, so what are the important things you want from a battery? You want to have higher voltage. Okay, so this is the y-axis. You want to have higher and higher voltages, and then wider voltage plateau. That means I want to, as the battery is discharging, I want to have constant voltage for a longer time. Okay, suddenly if the battery voltage goes down, that is not going to be a good battery. Okay, so I want to have a flatter voltage one, longer cycle life. I should be able to discharge it for 5,000 times. Okay, I want to just not use it for just few times. Okay, so these are things. So the way we try to look up, do it is, we try to explore different compounds, magnesium oxide compounds. Okay, so these are called polymorphic forms of MnO2. Whereas even though the chemical composition is the same, MnO2, you can make them, you can crystallize them in different crystallographic forms and control the voltage. And all these features can be controlled by crystallizing MnO2 in different forms. Okay, that's what we try to do. And what is important to understand is Prashant Gupta, he was an experimental battery scientist. Okay, he measured all these things. Aryan was an computational, he used the tools of computational quantum mechanics to compute the voltages. Okay, so this is the experimentally measured voltage profile. This is the experimentally measured voltage profile. As I said, it is not that by computations I'm able to get the exact voltage profile. That is not the role of computation. But what computations tell you is when there is a sudden change in voltage, the lithium binding sites change. Okay, I'm able to understand, correlate the change in voltage profile to some fundamental molecular things. Okay, this fundamental change in band till about 0.5. Okay, that is still about when battery is 50% discharge. The lithium binds in a particular place, but beyond this, the lithium binding sites change. Okay, this cannot be observed in experiments. So what maturity, what you should gain is what is to be measured and what is to be computed. That is something we should learn, okay, as researchers, as students, okay. So what the role of computation is not just to substitute experiment. It should give you insight, okay. When the voltage profile changes in a particular way, computations tell me why the voltage profile is changing, the way it is changing, okay. This can be measured experimentally, but the reason has to be understood computationally. Okay, we did this and so on. So typically, what the computations involve is how to find the lithium, where does the lithium bind, and the thermodynamics of the energetics and thermodynamics of lithium binding is what is obtained using computational quantum mechanics. Okay, so again, as I said, I can do, and then I can correlate with experiments. This is valence band XPS. This is a very powerful experimental tool. This is measured by Prashant, and this was computed by Aryan. Okay, so so you should know how to understand. So the Prashant and Aryan were a very good team because Prashant, being an experimentalist, he could understand the language used by the theorist Aryan. And Aryan could understand the language used by Prashant. Okay, so this thing is a skill set you should try to learn. If you go for coffee to the canteen, eventually the long door will be lifted and you'll be able to go. Always go with someone who has the complementary expertise. Okay, so you should be able to understand. If you're a theorist, you should be able to understand experiment on the other way around. This is a very important tool we should learn as a student, and also you can understand very fundamental aspects of lithium diffusion and so on. Okay? There are a few other things. These are all extremely interesting quantum mechanics called Yarn-Teller distortions and so on. One of the important challenge is why does the battery stop? I mean, why can't we use the battery all the time? When lithium intercalates with the cathode material, okay, in this case, manganese oxide, the volume changes significantly. Okay, this is not a reversible process. When the first time happens, 100 times happens, 1000th time it happens, the cathode material is changing gradually. Things are breaking down. There is fracture involved and so on. Okay, so it becomes less and less reversible. Okay, the battery voltage profile of the 100,000th cycle is different from what has happened in the first cycle and so on. Okay, this can also be understood from computations. Okay, so the last few slides I have. So what are the near-term challenges? Okay, in terms of a cathode, I want to utilize lithium to a greater extent. Okay, so Whittingham did a lot of things. Lithium intercalated in titanium sulfide. Okay, it's a very reversible battery. What do I mean by that? Lithium can go inside and come out without much changes for titanium sulfide. Okay, but for other cathode, dominant cathode, this doesn't happen. So while this happens, it gives you very less potential. That's why titanium sulfide was not used. For all these things, they give high voltages, but the lithium intercalation is not reversible. Okay, lithium, when it goes in and comes out, it changes. Okay, it fractures the material. Okay, there are lots of structural change. Okay, so you might have heard in your high school comes something called secondary battery and primary battery. Primary battery is used only for once. Okay, whereas secondary battery, you can rechargeable battery called secondary battery. We want to use it for many cycles. The number of cycle depends upon if the structural changes with lithium intercalation coming and going is less, then the cycle life is greater. Okay, so the ultimate battery is what is called lithium metal air battery. Okay, so I don't even use oxide. Lithium air goes, oxygen goes, binds to just form the lithium oxide and then comes out. Okay, this is an ultimate battery without involving sulfide, transition metal oxides, transmission sulfides. But this is one of the frontier topics. If we can master this technique, where I'm using less lithium metal as anode and air as a cathode, nothing to beat it. Okay, but this is frontier research topic. Okay, again, so what are the important research topics? Okay, so most of the research involved introducing different transition metal ions. Okay, called NMC, nickel, manganese, cobalt, everything in the periodic table in transition metal has been explored. It has been understood using computational quantum mechanics. Okay, so we are moving to anodes. Okay, last few things. What is the ultimate challenge in anodes? Okay, so the early lithium-ion batteries use anodes. Okay. These, whenever you use anodes, lithium metal as anode, it's a good material for Diwali. Okay, what do I mean? There are lots of safety issues. What is a safety issue? When lithium goes from the cathode during discharging and deposits on the anode, it doesn't deposit uniformly. Okay, so this is a very good paper, which is just a 4-page paper. You should all read. Okay, it's a very well explained. These structures, okay, these are rough structures. The non-uniform structures are called dendrites. Okay, this is what Professor Shobhit Omar talked about. Okay, so dendrites form, and ultimately what will happen is these dendrites, they can go and touch the cathode. When that happens, there is short circuiting of the anode with the cathode and the battery bursts. Okay, that's when the battery is used in Diwali. Okay, so that is a big issue. Okay, how to suppress dendrite formation is a topic of this. Okay, it's again an unsolved problem. If you can solve this problem, that's another Nobel Prize in waiting. Okay, so Yoshino, one of the 3 people who got the Nobel Prize, he worked did a lot of work in this area. He was the person who he got the idea of how to use lithium ion intercalated in graphite. Okay, that is his contribution for which he got Nobel Prize. This is an important housing problem. Okay, so there are lots of anode material. Instead of graphite, to increase the capacity, silicon has been used, germanium has been used, tin has been, lithium transition metal oxides has been used, and so on. A lot of important area of research. So if you can solve this problem, you're going to get a Nobel Prize. Okay, lithium metal without dendrites. Okay, that's a very, very important problem. Okay. And then solid state electrolyte. This is the third component. I talked about cathodes, I talked about the anodes. I'm talking about the solid state electrolytes. Okay, in our IIT-Kanpur is very strong in this area. In material science engineering, Professor Shobhit Omar and Professor Shikhar Jha, Shobhit has experience for 15 years. Shikhar has more than 5-6 years. Jishnu in mechanical engineering. He has used the tools of computation quantum mechanics to understand solid state electrolyte. This is a frontier topics in lithium ion batteries. Kantesh Balani, even though he's not worked in lithium ion batteries, he's an expert in, again, 15-20 years of experience in solid oxide fuel cells. Okay, much of the intuition which is being used in a fuel cell can be adapted for batteries. Okay, so so typically the electrolytes that are used in the modern batteries, okay, commercial batteries have lithium salt and organic electrolyte, non-aqueous electrolytes. People are trying to replace it with solid electrolyte. Okay, so you might have heard, okay, in one aircrafts which used solid lithium-ion batteries burst into flames during landing. Okay, that is because of this organic electrolyte. Lot of work has been is being attempted on how to use solid electrolytes. Solid electrolytes provide, it's a mechanical barrier for preventing dendrite growth. Professor Preetham Chakraborty from Aerospace Engineering is interested in problem. I'm working with Preetham on this areas. Okay, so how to improve solid state electrolytes? What are the structural motifs that increase the conductivity of solid electrolyte? That's an important area of research. In the interest of time, I'll summarize here. So the ideal battery, in my opinion, okay, in the next 10 to 20 years, this is where we are heading to, okay? So if you look at solar cells have a life of 20 years. One of the reasons is all the components are solids, okay? Whenever you have solids, there are reasons to expect greater life expectancy, right? So an ultimate battery would have all the three components, anodes, cathodes, okay, and the electrolytes to be solids, okay? So, but this is inherently a multi-scale problem, okay? If you're a person who is interested in mechanics, okay, if you're a mechanical engineer, aerospace engineer, there are problems for you, okay, in this area. There are lots of issues of fracture. If you're in material science engineering, working on applied mechanics, okay, there are very interesting problems involving when lithium goes and intercalates into the cathode and anode, there is fracture occurring, okay, plastic deformation occurring and so on. What is the issue? And if you're interested in quantum mechanics, okay, I've talked a lot about these kind of things. If you're interested in the mesoscopic microstructure in the battery, that is also, all these things can be done. Whatever is your interest, okay, if you're a chemist, physicist, engineer, batteries have something for you to answer. Okay, so this is an extremely interdisciplinary, exciting areas of research. In the interest of time, I would skip this. Okay, I wanted to contrast this research with another area. I still work a lot of this in difference in this area. Okay, so I want to talk about this. Okay, in the interest of time, I'll wrap up. Okay, I'll just okay. So just this is the last thing. So what I want you to understand, energy is not such a big challenge. Okay, a lot of energy is available in terms of solar energy. How do you convert that energy and store it? That is the grand challenge. Okay, if you're students, if you're thinking about Nobel Prize, that is where lots of important areas are going to be there. Okay, batteries. The drama is at many length scale. If you have interest in molecular length scale, mesoscopic, or continuum scale, batteries have something can challenge you. Okay, we work in lots of scientific faculty work in IIT-Kanpur. Mostly I talk about qualitative quantum mechanics in terms of band structure, how to go from chemistry to band structure to voltages. Lots of packages are available. Okay, density function theory is implemented. Therefore, even experimentalists can explore. Okay, Kantesh is an experimentalist. He's been using computation quantum mechanics to think about these things. I have not talked about electron transfer and transport. This is a fundamental aspects of physics. Quantum statistical mechanics can be used for understanding these things. So what you want to use these kind of techniques for rationalizing the important features of battery. You want to have higher voltage, flatter voltage profile. How do you increase energy, power of a battery? How do you increase cycle life? That's what I mean by rational material design. Okay, before you start doing experiments, you have to have a conceptual framework for designing material design. So near and long term, if you can have a lithium metal anode without batteries, without dendrites, and just air as the cathode, that's great. Okay, and most likely, if you can solve this, that will involve solid state batteries. Okay, that's an important goal. And as students, okay, you should know instead of asking. So you should develop an intuition for what is the important things to measure. If you have a quantity, whether it is better to compute it or measure it, okay, that maturity you should develop. If you're an experimenter, even if you cannot compute it, you can go and talk to your friend, okay, and say, can you compute this for me? And the other way around, okay. If you're a computational person, if you want an answer and that is better measured, you should be able to go and look at experiments. Okay, that kind of communication, that kind of maturity, you should be developed. You should be able to by the time you leave IIT-Kanpur as a researcher, you should be able to develop. Okay, that's the way most of the faculty we work. We don't work in islands. Okay, we collaborate and try to work together. Yeah, so it took more time. All right. Yeah, that's it. Yeah, if there are some questions, I can.
So thank you, Professor Pala. I think had it been a live session, you would be hearing a thunderous applause. But I think all are muted. So, so anyway, so any questions from the audience, then they can quickly ask. Yeah, please unmute yourself, Anurag, Mr. Anurag.
Hi, sir. I would like to ask a question.
You're not audible. Can you please be a little louder?
Yeah.
Hello. Can you hear me?
Yes.
Yeah, I can hear you.
There are two questions mainly. One is, does lithium, the size of lithium also play a role in the kinetics? For
Yeah, one at a time I'll answer. This is an important question. Lithium is very small. Okay, it's just hydrogen, helium, lithium, right? So that is an important, that's why lithium intercalation, when lithium goes, it should not change the host material by a lot. Compared to, see, we have lithium, sodium, potassium, rubidium, cesium, right? When you go from lithium ion battery to sodium ion battery, things change dramatically. Okay, the cycle life of sodium ion battery is less than lithium. So it is important, lithium being small plays an important role in both thermodynamics and kinetics. Yeah, next question.
sir, and also its speed. So does it, does the speed have a lot of effect on the degradation of the material, or is it due to chemical?
Yeah, it is true. If you can discharge the battery slowly, okay, then my cycle life has improved. Okay, if I want to, the difference between supercapacitors and batteries is the rate at which we discharge. Okay, so if I discharge the battery more and more rapidly, okay, cranking batteries, okay, they have lesser cycle life. But whereas if you can discharge slowly, my structural changes is lesser. Okay, my irreversibilities are lesser. My cycle life I can. Yeah, good. These are good questions.
Hello.
Yeah, is someone asking question? Who's asking? Vihan.
So, so I have a question, sir.
Yeah.
I think you can mute Vihan first.
Sure.
And yes.
I thought we were going to make it multilingual and have a Hindi question, but that's all right. Yeah. Carry on.
Hello.
Yeah.
Yes,
You can ask your question.
Yeah, Gaurav, please.
Yeah. Good evening, sir. That's really a very nice presentation. Am I audible? Can you hear me?
Yeah. Yeah.
Yeah. Okay. So I have two questions. So the first question is, it's regarding the design of the battery. So now currently we are looking for, like, we are now going from a rigid electronics to a flexible and a stretchable electronics. So since the cathode material here is a crystalline material and possesses a very brittle nature, so what's your opinion, and how can we design a material via computational methods or experimental methods for a flexible electronics? And second,
One at a time. One at a time. I'm not like Kantesh as a photographic memory. I have a very bad memory. I have the other extreme. Okay?
Yeah.
So I will tell you how to see. It's a very interesting question. Yoshino, the Japanese Nobel Prize winner, his advisor got Nobel Prize for discovering conducting polymers. The first anode that was explored was polyacetylene. Okay, it is a flexible conducting material that has lower energy density. That's why Yoshino didn't use polyacetylene and moved on to graphite to increase energy density. But that's a flexible material. So typically, when you even have a solid material, but when you use it as a thin film, okay, a few monolayers, things are usually flexible. Okay, but when you, the second question to answer is whether computational quantum mechanics will play a role. If you look at the history of quantum mechanics, the way it is implemented, it is more implementable in terms of solids. Okay, liquids are very hard to compute. The symmetry, the discrete translation symmetry, the unit cell concept that we have in solids have simplified the application of quantum mechanics. As soon as we go to liquids and amorphous material or conducting polymers, implementing quantum mechanics is hard, okay, but it is a frontier topic, okay. People are trying to do how to use quantum mechanics to understand metallic glasses, amorphous alloys, and liquids. It's being done. Yeah.
Yes, sir. Okay. The second question is somewhat relevant to this thing only. It's since you have discussed the solid state electrolyte. In that, as we have seen that during discharging, the lithium ion moves through the electrolyte to back to the cathode. So there is the transport in solid state electrolyte also. So I mean, I guess commercially what the batteries we are now using are LiPo-based batteries, the lithium polymer battery. So what is actually the transport mechanism in that?
These are important question. So these are not, these are semi-solid, okay. These are polymers. These are not like liquid electrolytes. They are semi-solid electrolytes. Understanding transport in solid electrolyte from quantum mechanics is not such a trivial issue, but people have tried to do it, okay. Especially there's a related problem called proton conduction in Nafion membrane, which is used in fuel cell. There, a lot more work has been done. Maybe you can mail me. It's a very detailed answer. I can send you some references.
Sure, sir. Thank you. Thank you so much.
But solid state electrolytes, see, there is a frontier, computational battery screening is done by Cedar, okay? Gerbrand Cedar, who was at MIT. He has a huge group and a huge company which screens materials, okay? He has done a lot of work. And Professor Jishnu Bhattacharya in mechanical engineering. He's, I think, academic grandson of Cedar. Okay, they have done some work and so on. So the mechanisms can be better understood in solid state electrolytes. I myself am more interested in solid state electrolytes compared to semi-solid electrolytes. There's a greater hope that you can understand it very well. I can send you some references if you email.
There's a question in the chat box. It's asking about the courses that a person should do to see or learn more about computational study of batteries related problems.
So this is partly an advertisement, okay? I'm offering a course, okay? And I think Somnath in material science engineering offers a course. When Professor Vishal Agarwal in chemical engineering, he offers a course. Our IIT-Kanpur engineering, that I'm addressing students, we have hired lots of people with good background in sciences, physics and chemistry. There are physicists who do Amit Agarwal, okay? He may offer courses in physics department. At a given time, our institute offers at least one course on computation quantum mechanics or molecular mechanisms, okay? Which gives you computation material science is being offered in mechanical engineering. In chemical engineering it's offered. It's surely offered in material science engineering, physics department, chemistry. Dr. Prasad in chemistry department, he is also offering. In MSP, we are planning to offer and so on. Okay? So you can send me a mail. Okay, so on all these things, I can look up the courses that are being offered, and I'm offering a course this semester.
I had one quick question on this. You were telling there's so much drama happening at different length scales. So what is main challenge at the continuum length scale, or maybe when you are really making a battery?
So how do you think about fracture, right? So when I see, there are two things. One is dendrite growth. These are problems which we are interested. See, there's the recurrent theme which occurs in many catalysis and batteries and so on. There's lithium binding and debinding. Okay, lithium binding and coming out, ion binding and coming out. Okay, is an important problem that can be addressed using continuum models, phase field models, mechanical engineering models. And then the other problem of dendrite, when there is electrodeposition, okay, deposition of lithium onto anode, okay, how does you use certain coating to suppress dendrites? Okay, there are a lot of mechanical barriers that are used. This is also an important problem. Okay? So lots of Preetham and we are trying to work on that. We've done some work in this. Okay, myself, Preetham and Jishnu, we worked on a problem we published also last year. When lithium goes and binds to silicon and germanium, after some times it fractures. Okay, so we looked at the mechanics of this problem.
So I don't see any more questions. So I really thank Professor Rajpala for bringing also so much humor during his talk. And from Material Advantage, we have a mug for him. I just opened it. It says Material Advantage. And thanks for delivering this.
There's an online mug.
Yeah, I'll bring it to you sometime.
No, just kidding. Yeah. All right. Thanks a lot for. Sorry that I went.
Thanks to Shruti for, I think, initiating this as well and assisting with. And also, I thank all the participants who have been here and patiently they waited till the end. I think it is almost, I think, 1.5 to 2 hours. So thanks for staying.
1.5 hours. Okay. So one thing, Kantesh, just for what I can do is I can send a PDF of these slides to you. In case somebody wants it, they can either mail me or you.
Okay, great. Thanks a lot.
And if you have any questions, you can.
So thanks, Professor Pala will be available for any queries. If someone has, they can directly email him. And thanks a lot. And I think we'll now end this lecture. Thanks a lot, Professor Pala. Thanks a lot.
Thanks. Bye.
Thank you, sir. Thank you.